All right, so today we're going to review chapter 12 materials using that version 2 review document. And as usual, I've highlighted some that I want to get to. But you can stop me anytime if there's one in particular that you want to deal with. And then we'll go in and do our chemical kinetics lab. Next week, I'll hand out the lab number 3, and that'll be the lab we do after we come back from spring break on the 17th. So you'll have a couple of weeks to put this kinetics lab together in a report. You might need it. And even though we're going to be on spring break, you can email me, or we can set up a meeting if you have trouble with it. All right. I may not be on campus, but I'll be available. All right. Let's take a look at number 1. Let's see, I've got till 10:25. Okay. Based on this reaction, so we've got hydrogen peroxide and iodine, and 2 hydrogens yields this ion plus water. And that should be balanced. Just do a quick check. Yeah, 2 hydrogens here and 2 there, so we're good. All right, I'm satisfied. If the reaction is first order in this component and second order in this component and 0 order in that component, which the following rate law would be preferred format. And remember the rate, we just say rate because the rate can be whatever units you decide. And then we have rate constant. And then we have the concentration of this component, which it said was second order, right? Second order. And this one's first order. And this one's 0 order. Right? We don't have to write the 1 there because it's understood. All right. Preferred rate law. If that's 0 order, that's equal to 1. So we don't even need it. That would be the preferred form for this rate law. And if you're wondering what happens to that in the rate law expression, well, if it's 1, it doesn't need to be there, right? And if you're questioning yourself about why isn't it there, I mean, it's in the balanced equation. Well, you can see that all these components are there, but you can see this one's missing in your rate law, so you have to assume that it's 0 order. All right, so that's E would be the answer for that one. All right, number 2. It's not erasing very well. Okay. Let me get something in between here. I might have to do some quick maintenance on this board. Here. Thank you, polish. Let me use this. The idea is to seal the pores. so the marker doesn't embed itself in the board. Sort of glides on the surface. WD-40 will do that too. All right. Let's see what that guy's. 2. A reaction has the rate law. Let's see, 2, 1, and 2. Rate equals K, and then A to the second order, B to the first order, and C to the second order. Okay, what's the overall order of the reaction? Not a trick question. What's the overall order of any reaction? It's the sum of the individual orders. 2 plus 1 plus 2. It's 5. That's the overall order for the reaction. The order for A is 2. Order for B is 1. Order for C is 2. That's how they respond in the reaction. But the overall order is 5. Let's see. We might come back to that one if we get time. In the meantime, that's a little better. Let's see. We're down to 4. Yeah, 4. If this reaction is second order, so we've got 2 hydrogen iodide yields H2 and I2. And it's second order. All we have to say is second order because we usually define a reaction in terms of disappearance of reactants. So we've only got one reactant. That means we would say, well, let's see. What's the question? Which of the following will yield a linear plot? Okay. So if we were to conduct this experiment ourselves, we would have a data set where we would have time and we would have concentration of hydrogen iodide over time, and it would gradually get lower. And we could plot those two. But if it's second order, what are you going to get out of this one? A curve, right? A decreasing curve. All right. So what do we do next? Well, we take the natural log of HI. Right? What do you get when you plot this one and this one? If it's second order, you get another curve. Right? Then what do you have? Well, you can take the inverse of HI and plot those. Okay. What do you get with that one if it's second order? 1 over HI. You get a straight line. Okay. Yeah, if it's second order, if it's zero order, this gives you a straight line. If it's first order, that one gives you a straight line. With both of these have negative slopes. But when you invert it, you also invert the nature of the slope. So for second order, that would give you a straight line. So the answer there would be B. You just plot the inverse of HI, concentration versus time. And that'll give you a straight line. Now, what if you have more than one reactant? That won't work unless you can do something about the second or third reactants. Just make them so high in concentration that they don't change during the reaction. That's what we're going to do today. Okay, number 5. Which of the following statements about enzymes is incorrect? Okay. Well, let's see. We got A, B, C, D, and E. Yeah, all of these are correct. All right, so we got to look at all of them to be sure. Enzymes, they are usually proteins that catalyze specific biological reactions. That's true. They are usually proteins. There are some known enzymes that are RNA. If you've had biology class, you should have been introduced to DNA, RNA, and that type of stuff. But most of them are proteins. B, they are equal to inorganic catalyst in efficiency. That's false. In fact, they are more efficient than inorganic catalysts by orders of magnitude. Much, much more efficient. Okay, so E can't be it either, because we found one that's wrong. And that should be our correct answer. Several thousand are now known. Yeah. In fact, it may be in the tens of thousands by now. The molecules they react with are called substrates. Yeah, we didn't cover that in class, but that's true. The substrate of an enzyme is that molecule upon which the enzyme works. Now, it doesn't have to be just one substrate. A lot of times it is just one. But just as often, you may have two substrates that normally would enter into a chemical reaction, and the enzyme attaches itself to both of them. We won't go into the details there about the lock and key theory, but they are called substrates. All right, how about number 8? A little better, but not much. Maybe the camera won't pick it up. A free radical is a chemical species that possesses what? You remember that? I'm sorry? Yeah, possibly. Which one is it? Yeah, unpaired electron. That's a free radical. Any atom or molecule of any kind that has an unpaired electron is extremely reactive. Those free radicals wreak havoc on just about any system where they're found. Free radicals in your body damage DNA. That's why there's such a push for nutrition that you consume free radical scavengers, such as unsaturated fatty acids. Vitamin C is a very good free radical scavenger. Right? And free radicals in your body are often an indication of inflammation or tissue damage. Produce free radicals. So if you've got a cold or some type of illness, then vitamin C can help a lot because it'll scavenge those byproducts of cellular breakdown. And then there are other possibilities like free radical catalysts in the upper atmosphere destroying the ozone. Right. I think we mentioned that in first semester or this semester. I think it was first semester, wasn't it? Yeah. Oh, excuse me. Okay, so D is the answer. Number 9. The rate expression for a particular reaction is first order, second order. Rate equals K. A first order, second order. Okay. If the initial concentration of B is increased by 0.1 molar to 0.4 molar, so B is going to go from 0.1 molar to 0.4 molar, is it? Yeah. This is one experiment This is a different experiment. Okay. In the first experiment, we have 0.1 molar for B and 0.4 molar in the second experiment. The initial rate will increase by which of the following factors? Well, all you have to do is see what order it is, right? How did this change? It increased how many times? Factor of 4, right? This is an increase of 4 times concentration. The effect it has on the rate is squared of 4, or 16. Okay. And the overall rate, if you leave this one constant, of course, that's the effect. If this one changes also, say it went from 0.1 to 0.4, it would be 4 times, simply to the first power. And then overall, it'd be 4 times 16 would be 64 times. If you increase this one by the same amount, you increase that one. That wasn't in the problem, but I thought I'd take advantage of the situation. Number 10. For which order reaction is the half-life of the reaction proportional to 1 over K? Okay, half-lives. If we have 0 order, first order, or second order, half-life expression for each one. And to be honest with you, if you don't use them every day, they just kind of fade. So I'm going to look them up because they should be in useful information. Here we go. So half-lives. Here we go. A over 2K. So this one is half-life equals concentration, initial concentration over 2K. This one, half-life equals 0.693, I think, over K. Yeah, and the last one is 1 over 1 over.
And it shows you didn't get the question.
I'm sorry?
Didn't get the question. 10 and 11.
Oh, am I answering the wrong question? Oh, let's do 10 and then we'll look at 11 to see if it is a repeat. Could be. Let's see, K times 80. There we go. Okay, so these are the half-life expressions for each of the order reactions. Which one is proportional to 1 over K? All of them. They're all proportional to 1 over K. We just throw in some other factors along the way. Okay, so D is the answer for that one. Let's see. For which order reaction is the half-life of the reaction proportional to 1 over K? K is, yeah. 11 is a duplicate. All right. Moving on. Number 13. Of the following choices, which type of collision is the most likely to be the rate determining step in a proposed mechanism? Well, the point of this question is, which one is the slowest of all those? All right. D, non-molecular, is just stupid. I had to put 5 selections in there, and I didn't want to put, none of these is already in there, and I didn't want to put 2 of these or one, or so I just made something up. So we're really looking at A, B, and C. Which one of these, if they're present in any mechanism, all 3 of them, which one would be the slowest? The least likely would be the slowest. Right? unimolecular is more likely than bimolecular, and bimolecular is more likely than termolecular. Termolecular almost never happens because it's very difficult to get three species together at the same time with the proper orientation and energies to accomplish an elementary step reaction. So C is your answer. Termolecular is definitely the slowest possibility of all those. Let's see. Okay, 14. All right, the reaction, hydrogen peroxide yields 2 water plus O2. Has the following mechanism. Okay, this is uncatalyzed. Oh, wait a minute. No, it's not. It's given us an elementary step. Oh, it's introducing some other factor in there. All right, first step is we take one of these plus an iodide ion, and we produce water. And is it OI or IO? IO minus. And then the second step is we take another one of those hydrogen peroxide and we combine it with that species and produce water. So there's our other water. There's our 2 peroxides and oxygen and iodide. Excuse me, iodide ion. So which in this, if this is the mechanism, actually, I think the mechanism for that this one is addressing is more complex than that, but this is one proposed mechanism. So what we're focusing on is what's the catalyst? A catalyst is a species that goes in the front and comes out the end, and it looks like it never changed. Right? So iodide goes in the front and it comes out the end. That's the catalyst. Okay. While we're here, what's the intermediate? The intermediate is something that is produced in the elementary steps, but never shows up as a product. So this would be an intermediate here. It's consumed here. It's not in the products. Okay, that's an intermediate versus catalyst. Catalyst comes in the front door, goes out the back door, and you don't know what happened inside. The intermediate, you don't even see an intermediate most of the time. It's possible with laser technology and fast electronics to pick up the signature of some intermediates during a reaction. But it takes an expert with expensive equipment to do it. All right. Let's see, we're going to skip that one and go down to this one. I'm pretty sure I've got an initial rates one in here. We skipped over 1 or 2 of them already, but we'll definitely get to an initial rates problem in a minute. Number 17. What's the order of the rate law with respect to MnO4 minus? Oh, that must be what we're into now. So this is the initial rate equation, initial rate experiments, 4 of them for the reaction as given. All right, let's move this up out of the way. And our reaction is 2 MnO4 minus 4 minus plus H2C2O4 2O4 and plus the third component is, and since this is initial rates, we don't care what the product is, except now that the equation is balanced, we don't have to consider them. Okay, but we do need them to balance the equation. It's just that after the equation is balanced, then we can go ahead with just these components. All right, so these experiments, 1, 2, how many should I have? 1, 2, 3 plus 1 is 4. I need 4 experiments with 3 reactants. Okay. So the data we collected was for this concentration, 1 times 10 to the minus 3 molar. And this one also 1 times 10 to the minus 3 molar. And this one, 1 molar. Okay. That's an extremely acidic environment. 1 molar hydrogens. Oh, yeah. The other 3 are all 2 times 10 to the minus 3. Okay. And the second one for, I think this is oxalic acid, is 1 times 10 to the minus 3. And then these are also 10 to the minus 3, 2 times. Okay. And then the last one is 1, 1, and 2. And then the rates are given for each one of these in molarity per second. 2 times 10 to the minus 4. I could read it easier here. 8 times 10 to the minus 4. 1.6 times 10 to the minus 3. And 1.6 times 10. Okay. So what you'll notice is that we've set up 4 experiments so that we can hold 2 of the reactants constant while the third one varies. So if we hold this one the same for these 2, and these 2, this one varies. That's how we get a handle on the order of this one. And I think that was the question. Yeah, we want to use these 2 to find out what the order of that one is. So if we write the rate law, we can say the rate for, let's do number 2. And the reason I do number 2 on top, I'm going to do the ratio thing. 2 on top is because it's bigger than the one on the 1. And when we do the ratio, then we get a whole number and not a fraction. So the rate for number 2, we're going to ratio for the rate with the rate for number 1. And that's equal to 8 times 10 to the minus 4 molarity per second divided by 2 times 10 to the minus 4 molarity per second. And this is equal to, right, the rate expression for 2, the rate expression for 1. So we have this one where we got, I'm going to actually put the values in here. We would put MnO4 minus to the n power. But this is 2 times 10 to the minus 3 to the n. And this one, in this reaction, is 1 times 10 to the minus 3 to the n power. And then these, I'll just go ahead and put all of them in there. 1 times 10 to the minus 3 to the m power for that, for oxalic acid, and 1 times 10 to the minus 3 to the n. And this one is 1 to the, let's see, we use P, don't we? Instead of O. Hey, there we go. So that's our ratio to find out what's the order for MnO4 minus. Okay. These are going to cancel. They're exactly the same. Oh, I left out K. K cancels because it's the same for both of them. And now we have 2 times 10 to the minus 4 into 8 times 10 to the minus 4 is 4, correct? Okay. So the only terms left on this side are 2 divided by 1 to the n power. And you know that if this one's to the n power and that one's to the n power, then we can divide them and the whole thing is to the n power. I forget what rule that is, but it's true. So 2 divided by 1 to the n power. 2 to the n power is equal to 4, so n has to be equal to 2. MnO4 is second order. Okay, you can do that to all three of them. If the question asks for one of the others, you just take, say if you want to find out this one, you need experiments in which these two remain constant and this one varies. So you'd use 3 and 2 expression here. And that would be 1.6 divided by 8. Well, 1.6 to the 10 to the minus 3, 10 to the minus 4, it would be 16, wouldn't it? So it'd be 16 divided by 8 would be 2. And let's see, these two. 2 divided by 1 is 2. So 2 to what power is 2? First power. So this one's the first order. And then if we let this one change, and these stay constant, then we have 1.6 divided by 1.6 is 1. And then 2 divided by 1 to the p power is equal to 1. So p would have to be equal to 0. That's the only way you get 2 equal to 1 is take it to the 0 power. And then once you've got all your, let's just go ahead and do that. Let's see. Rate expression. I'll erase this. So the overall rate expression for this equation would be K and MnO4 minus to the second power and H2C2O4 the first power, and then we just leave hydrogens off because it's 0 power. So what would K be equal to? All you'd have to do is just take one of these rates, one of these experiments, plug in the values. Say the rate for the first one is 2 times 10 to the minus 4 equals K. And this would be 1 times 10 to the minus 3 squared. And this would be 1 times 10 to the minus 3 to the first power. And solve for K. Right. Then you've got all the terms you need to write the complete rate law for this equation based upon the method of initial rates. Or say if I gave you a question on an exam and it says, this is the rate law and the K is still unknown. You take the initial rate data and take the equation as given, if I've given you all the orders already, and tell me what K is. That's how you would do it. Okay, so C is the correct answer. Let's see. Yeah, I think 18 stands alone. That diagram goes for the following ones. Actually, that should be 19 and 20, shouldn't it? Not 8 and 9. Forgot to change that part when I spliced them together. Okay, let's go to 18. All right. The rate law for the reaction 2 nitrogen monoxide plus 1 oxygen yields 2 nitrogen dioxide. So that rate law is K rate equals K times NO second power. Yep, second power. And O2 the first power. Okay, what happens to the rate when the concentration of O2 is tripled? Oh, we've done one like this already. when you triple the concentration of this one, you triple the concentration of that one because it's the first power. The rate triples. Okay. Oh, we're gonna skip that one. Or do we have another one down there with it? 19 and 20. If we don't find one, but we'll come back to that one. Because that's an important concept. Since I didn't highlight it, we'll go to the next highlighted one. Here we go. 24. What fraction of a reactant remains after 5 half-lives of a first order reaction? Okay. Do we need all that information that's given in the question? What fraction of a reactant remains after 5 half-lives? Doesn't matter what the order is. The order tells you what the half-life actually is and relates it to other factors in the equation. But the half-lives are, it doesn't matter if it's a chemical reaction or a nuclear decay. The half-life is the half-life, and it just means after one half-life, you've only got half of the original left, right? So after one half-life, let's say 1, 2, 3, 4, 5, right? 5 half-lives. Okay, here's the original amount. So after one half-life, you have 1/2 of that left, right? After the next half-life, you have a half of that left, which is 1/4 of the original. After this half-life, you have a half of that left, which is 1/8 of that left over. And half of that is 1/16, and half of that is 1/32. So after 5 half-lives, you've only got 1/32 of X left over. A quicker way to do that. How many half-lives? 5. 2 to the 5th power reciprocal. Okay, so 2 times 2, let's see, that's half. 1, 2, 3, 4, 5. So 2 to the 5th power is 32. And 1 divided by 32 is that. So it works either way. All right. So that was E. Okay, let's take this equation for 25. Two A sub 2 and B sub 2. 2A, so that's diatomic. That's diatomic. Excuse me. Gives you 2C. So the first step is fast. Step number 1 is fast. And it's A sub 2, B sub 2 yields C. And the second one is very slow. Ooh, that put 2 there. First one. Very slow is A sub 2 plus R. Oh, I left out R plus R. Left out my intermediate. There we go. So, what's the question? Which step is rate determining? All right, that's simple. It's the slowest one. That's the rate determining step. But is this a valid, are these valid elementary steps? Is this a mechanism that's valid? Well, first of all, you have to add them up, right? 2 A2s and a B2. R's on both sides. These are intermediates cancel. Yields 2C. Yep. As far as that goes, it's valid. we don't have a rate expression for this one, so we can't test the elementary steps to determine if it's the correct rate expression, but that's what you would do. Once you have an experimentally determined rate equation for this one, then you go to your elementary steps and create a rate expression from the elementary steps and see if they match. All right. 26. For a reaction A yields products. And the initial concentration of A is 6.4 molar. All right, let's set up as a table. So the concentration of A, the initial concentration is 6.4 molar. 6.4 molar at time 0 at the very beginning. The first two half-lives are 60 and 30. So the first two half-lives are 60 minutes or seconds? Minutes. Okay. So after 60 minutes, we have 3.2 molar left. The second half-life is based on this amount, and it's only 30 minutes. So this is T1/2. It's 60 minutes, 30 minutes. And this would be 30 minutes further. So after 90 minutes, we have half of this one left. So that'd be 1.6. Yeah, that's half of 3.2. So that's what the problem is telling us. If this reaction is known to be 0 order, what's K? This is 0 order. That means the rate equals K times A to the 0 power. Right? So it's actually the rate equals K. Doesn't matter what that is. But that's not going to help us any. What we need is to use the half-life for 0 order. Right, so I got to go back and look again. A0 over 2K. So the half-life equals A0 over 2K. There we go. So if we take the first half-life here is 60 minutes. I'm going to do both of them. 6.4 divided by 2K. Then we solve for K. Bring the K over here. Bring 60 over there. And that's 6.4 divided by 120. Right? Get my calculator. Or did I go too fast on that step? We're good? Okay. So 6.4 divided by 120 is 5.33 times 10 to the minus 2. Now let's see if it works. 30 minutes equals 3.2 divided by 2. Okay. All right. So if we bring K over here and put 30 over there times 2 is 60. 3.2 divided by 60 is 5.33 times 10 to the minus 2. Okay, I was just checking to see if they're honest. So C is the answer. We found out what our K is. Yeah, I just said calculate K without units. So the rate would be that value. that would be your rate equation, just be that K value. If it's zero order. Right. 26. Here. All right. Next. Okay. 31. The rate constants for a reaction at two different temperatures are given below. What's the activation energy for this reaction? All right, so I got to look up that equation. At two different temperatures. Okay, so I've got two possible equations in here. And the one that we would apply is log K2 over K1. Equals E sub A over R times, let's see, is it plus or minus? Minus T1, T2. There we go. Okay, so we're given this data. Temperature 1 is 30 degrees. So what's K2? K2 is 1.21 times 10 to the minus 3. And K1 is 1.38 times 10 to the minus 4. Okay. E sub A is what we're after. R is what? 8.3145. It's the one that has joules in it. Okay. And then this one is 1 over T1 is 30 degrees, but it has to be Kelvin. So it's 30 plus 273 minus 1 over 49 plus 273. There you go. Now we got the equation set up. So I'm going to say 1.21 exponent 3 divided by 1.38 exponent times 4. So that's the natural log of 8.7681 equals E sub A, do it in stages. 30 plus 273 is 303. So the reciprocal of 303, which is what that means, 1 divided by 303, is 3.30 times 10 to the minus 3. And minus, then 49 plus 273 is 322. We'll take the reciprocal of that, and we get 3.11 times 10 to the minus 3. Okay, subtract that one from this one, and I've already got it in my calculator, so I'm just going to hit the minus button. This 1.947 times 10 to the minus 4. Okay. What's the natural log of 8.7681? Scroll back to that one. Find the LN key. There it is. This is 2.171. This is in the denominator. So I'm going to multiply those two together. 3.145. equals E sub A times 1.947 times 10 to the minus 4. And actually, this is in the numerator, just bring it over here in the denominator. Like that. Okay, there's actually that. This. Just cross that one. Okay, so I got 2, I got 8.3145 times that and divided by 1.947. And I get E sub A equals 9.27 times 10 to the 4th. Oh, standard notation. All right, this is joules. Activation unit joules. Actually, joules per mole. And the answers are all in kilojoules per mole. Okay. So let's do this. Which way would the decimal move if we're putting standard notation? If this gets smaller, that's got to get bigger, so it has to move to the right. Okay. 27000. Just put a bunch of zeros out there. Okay, we'll go 1, 2, 3, 4. Right here. Okay. Actually, I don't need a decimal because those two are not significant. That's joules. Kilojoules would be 1,000th of that. Kilo would be 1,000 times it gets bigger, the unit gets bigger. So this has to get smaller by 1, 2, 3. So it's 92.7 kilojoules per mole. That would be B. Okay. Heavy math in that one. Not 32. Oh, that was that was a modification of the Arrhenius equation. In case you want to look it up. Uh, 32. All right. Consider the following balanced equation and the experimental results that follow. This is another initial rates equation. What are the rate law orders of NO and H2? So this one shouldn't be too bad. It's only got 2 reactants. 2 NO. I'm gonna leave off the phases. 2H2 yields something into plus 2H2O. So let's put the rate under here. And experiment number 1, number 2, number 3. Right? 2 plus 1 is 3. So what are the concentrations for these guys? 0.015 and 0.020. 0.015 and 0.020 molar. 0.6. 0.60 molarity per minute. And these are molar. Okay, second one. 0.015 and 0.040. And 0.040. What's the rate for this one? 1.2. And the last one. 0.3 and 0.2. 0.3. 0.30, I think. Yeah. And 0.020. And this rate is 2.4. Okay. So our rate law is going to look like this. Rate equals K NO to the N and H2 to the N. Fix that. All right, so when we ratio them, if we do the first one, we want to let this one change and keep that one constant. So this one changes from here to here, and that one's constant from there to there. Okay, so we're going to use number 3 ratio to number 1. Okay. So the rate for number 3 is 2.40, and the rate for number 1 is 0.60. That's equal to K divided by K, and then this value here, 0.03 to the N, and this one 0.015 to the N. And then these two are going to cancel because they're exactly the same. So really what we have is what's 0.6 into 2.4? This many. 4. And 0.015 divided into 0.030 is 2 to the N, so N equals 2. Now we can change this to, and we just have to set up to do where this one is constant and that one changes, which is 2 and 1. So we'll do 2, which is 1.20. And then this is going to be the same, but this one we allow to change from 0.040, 0.2020 to the M in M. So now that these two cancel, 1.2, that's 2 equals, and this is 0.020. There we go. So that's 2 to the M. Right? M equals 1. So all we have to do is just erase that. And what was the question again? Orders of NO and H2. So it's 2 and 1. That's C. Okay. Who's next? C, 33. The first order decomposition of H2O2 at minus 28 degrees occurs with a half-life of 50 seconds. Starting with a concentration of 25.2 molar, what will be the residual concentration of H2O2 after 5 minutes? Okay, let's put what we've got up here. Temperature equals minus 28 degrees C, is it? Yeah. First order, so decomposition of H2O2 would be rate equals K H2O2 to the first order. Yeah. And the first half-life equals 50 seconds. Okay. If you start with a concentration of 25.2, so the starting concentration is going to be 25.2 molar. What's the concentration after 5 minutes? Okay. So change in time is 5 minutes. Okay, that's everything that we're given. Right. What do we need to solve this equation? We need an equation that has time in the expression. In the first order expression, we're talking about an integrated rate law, not the differential. The integrated rate law here in useful information, there's a zero order, first order is the natural log. So the natural log of H2O2 equals minus K T plus the natural log of the initial concentration. Okay, I think that's right. Yeah. And the half-life expression for that is 0.693 divided by K. So T 1/2 equals 0.693 divided by K. We need this because we've got to have K. We can't solve this equation without K. So the half-life is 50 seconds. 0.693 divided by K. So K is equal to 0.693 divided by 50 seconds. Now let's look at it. Okay. We'll leave it in seconds. So let's find out what K is. 0.693 divided by 50 is 1.39 times 10 to the minus 2. That's K. So we have minus 1.39 times 10 to the minus 2. Then we need to fill in the time in seconds. And then the natural log of our starting concentration is 25.2 molar. Okay. Our final concentration is, we don't know. That's the answer. What we need is, what's the T? If we're starting from here at time 0, after 5 minutes, how many seconds is that? 60 seconds in a minute? 300 seconds, right? 60 times 5. No arguments, okay. So that goes in here. It has to be seconds because of the way we calculated the K. Okay, now we can get the right-hand side of the equation. I'm just going to change the sign. I've already got 1.39 times 10 to the minus 2. I'm going to change the sign, times 300. And then I'm going to take the log of 25.2, the natural log, 25.2, and add that. So this side is minus 9.31 times 10 to the minus 1. And that's that. So how do we get this value? Well, this is equal to the anti-natural log of that value. So I've already got the value in here. I just need to find the anti-log. What's the anti-log of Ln? It's e to the x on my calculator. So let's see, I just need to go here, go that. And let's see, is it in standard notation? Yes. Okay, so this concentration after 5 minutes is 0.394 molar. So it went all the way from 25 molar down to less than 1. And that's C. Okay. All right. Next. 34. For the second order reaction, NO plus O3 yields NO2 plus O2. The rate constant has been measured to be 1.08 times 10 to the 7th at 298 K, and the activation energy has been measured at 11.4 over the temperature range 195 to 304. So we're within that range at 298 K. What's the rate constant at 233 K? All right. So I think we go to that same Arrhenius equation, right? We have, well, let's put this up here. The rate constant at 298 K, 1.08 times 10 to the 7th. So the K at 298 K, correct? Yeah. It's been measured at 1.08 times 10 to the 7th. Times 10 to the 7th. We want to know the K at 233. 233 K. That's the question. Let's do this. Okay. What else do we know? Well, we know the rate constant for that one. And we know the activation energy is 11.4. So E sub A equals 11.4 kilojoules per mole. And R equals 8.3145 joules per mole K. The reason I put that up there is to emphasize the constant is in joules, that's in kilojoules. So we got to change it. Has to be joules. So the way I do it is 11.4 times 10 to the 3rd joules per mole. Right? I just take the kilo, and what does the kilo mean? It means 1,000. So I plug the 1,000 in here. And you can put that into your calculator just like that if you want. It doesn't have to be scientific notation. Now we need the integrated. Let me just put this up. Save me some walk. I don't have it memorized, so I can't expect you to have it memorized too. Okay, so we have natural log of the ratio of the K2 to K1. So this is K2. This is K1. Equals E sub A over R and 1 over T1 minus 1 over T2. So now we can put these values in. Well, we put the ones we know. This one is unknown. This one is 1.08 times 10 to the 7th. This one is 11.4 times 10 to the 3rd. And this is 8.3145. And then 1 over T1 is 298. And then 1 over 233. There we go. So now we have to solve for this one right here. Did I set it up right? Okay. Let's see. 298, take the reciprocal, and 233, take the reciprocal and subtract. So this right here is 3.019 times 10 to the minus 2. And that can be multiplied by this and divided by that. Times and then 8.3115 divide. So this value over here is 41.39. Okay. Now, how do we get this apart? Well, you have to remember your log rules, right? The log of A over B is the same as the log of A minus the log of B. So we're going to say the log of K2 minus the log of 1.08 times 10 to the 7th. There we go. So we can take this value and add it to both sides. So the log of K2 equals 41.39 plus the log of 1.08 times 10 to the 7th. Let's see, I gotta punch that one in again. 1.08, 0.7, and take the log of it, which is 16.195. 16.195 plus 41.39. Which is 57.58. So now all I have to do is take the anti-log of 57.58 or e to the x, and that'll give me K2. Ooh, that's big. And it's nowhere near the correct answer. So I made a mistake somewhere. Let me see where it is. Nick 10 to the 7th. I'm good down to here. 41.39. Oh, I messed that up. Do this calculation again. I think that's where I messed up. So 298, let's see. T1, yeah, minus T2. 298, take the inverse. And 233, take the inverse and subtract. Oh, that's it. This is minus 9.36 times 10 to the minus 4. So this value is going to be here. This value is going to be different. This value is going to be different. Okay, so I'm going to take that times this 11.4 exponent 3 and 8.3145 divide. Okay, so this is minus 1.284. And then I'll take 284. Then I'll take, oh, this one, I've already been given that one, right? 16.195. Okay, 14.91. And then take the anti-log of that, which is 2.99 times 10 to the minus 6. So K2 equals 2.99 times 10 to the 6th. Close enough. C is the closest one to that. I think what I did over here was I took a reciprocal of a reciprocal. I think that's what happened. And it's easy to do. Check yourself. It was obvious I made a mistake because my answer was none of the selections. So whoever set this question up didn't anticipate that mistake. Let's see. Where are we going from here? Oh, okay. We don't have to go back. We do have one that addresses that question that I was wanting to pose? I think I'll leave that mistake in. That was good teachable. When I post a recording. Okay. Let me make that smaller. Don't make it too small. I want to be able to answer those three questions. All right. This is a potential energy diagram, and I'll just rough it out. This is the energy, total energy of all the reactants and products. And if we start off at this level, then we have to go up for any collision that occurs. You need at least this much energy for the reaction to proceed. Okay. So this is the uncatalyzed reaction. And this distance between here and here is the activation energy for the uncatalyzed reaction. So the uncatalyzed reaction would be E. Without use of a catalyst would be E. That's 39. Let's see, I think I got 40 and 41. Okay. Which letter shows the activation energy with the catalyst? That's the one that has a lower activation energy. Like that. Why does it do that? Why does it have a lower activation energy? Because it uses a different mechanism. The elementary steps are completely different for this reaction sequence than for this one. So that would be A on your diagram. A would be the activation energy for the catalyzed reaction. And then the last one, which letter shows the activation energy for the reverse reaction? Okay. If you're going backwards from products to reactants, you've got a distance from here to here. Activation energy reverse. Okay. And on our diagram, that's B. No, C, excuse me. C. Yeah, C. Now, while we're here, what would be the enthalpy of that reaction? The difference in energy between the reactants and products. So final minus initial. Products are a smaller value minus reactants, which are a bigger value, which gives you a minus value, right? So it's exothermic. And that difference is F. The delta H would be F on this diagram. All right. That's not one of the questions, but I thought I'd throw it in. Okay. What was the value of the rate constant? Okay, disorder. Okay, I think these are the last two. Yep, last two are based upon this diagram. All right. So let's clear the board. And we don't have to backtrack any because we got the one that I wanted. It showed up in two different places. Okay. So look at this plot. You've got the concentration of SO2 CL2 in this reaction, and the reaction is not specified. It's just the disappearance of that compound. Okay. So that means its concentration goes down over time. And if we plot, let's see, 42 and 43. if we plot the data and we get a straight line, what order of this reaction is there? Well, if we write the rate equation, the rate equals K times SO2 CL2 to the first order, right? First order is natural log plot of time and the against time. Gives you a straight line. So we know it's first order. We solved that problem. What's the order in the reaction? It's first order. Right? So that's 42. What's the value of the rate constant K? Okay, if we look at the integrated rate law for this one, the natural log of that term equals minus K T plus natural log of that term initial. So this is the slope of the line. Minus K is the slope of the line. The slope of the line is, there's the equation in the upper right-hand corner. So the Y is this term, the B is this term, and there's the slope. Minus 2.20, minus 2.20 times 10 to the minus 5. That's equal to minus K. So here's your K right there. That's K, 2.20 times 10 to the minus 5. B is your answer. Okay. All right. Ooh, we're finished early. Questions?